Your application is waiting unnecessarily for independent data fetches. Sequential await forces serialization of input-output operations. Consider this common pattern. Await fetch user, await fetch products. If fetching user data takes 500 milliseconds, the product fetch waits. If the product fetch also takes 500 milliseconds, the total execution time approaches 1 full second. The await keyword pauses the surrounding async function entirely. This pause serializes tasks that do not depend on each other's results. This unnecessary serialization directly increases the total wall clock time required. We must initiate these independent tasks concurrently to minimize perceived latency. This is the only way to achieve true performance gains in modern web applications. The mechanism for concurrent execution is the Promise.all method. Promise.all accepts an iterable of promises as its single argument. It returns a single promise that manages the entire group of tasks. All input promises are initiated simultaneously upon calling Promise.all. This immediate initiation achieves true parallel execution of asynchronous tasks. The returned promise resolves only when every single input promise has successfully resolved. The result value is an array containing the results of all input promises. The result order strictly maintains the order of the input iterable. This ordering is preserved regardless of individual promise completion times. This pattern ensures the total execution time approximates the duration of the longest-running task. To execute two async functions in parallel, invoke them immediately without a wait. Define the promise objects like this: const p1 equals f1f, const p2 equals f2f. This crucial step initiates both asynchronous tasks concurrently. Next, pass these resulting promise objects directly to Promise.all. Use array destructuring to capture the results cleanly and efficiently. The syntax is const r1, r2 equals await Promise.all p1, p2. This pattern ensures the total execution time approximates the duration of the longest-running task. We are concurrently fetching configuration settings and user profile data. This reduces the total time from the sum of T1 and T2 down to T maximum. This is the correct way to maximize throughput in your JavaScript applications. Promise.all operates strictly on a fail-fast principle. If any single promise within the input iterable rejects, the entire operation stops immediately. The Promise.all promise rejects with the reason of that very first rejection. Results from all other promises are discarded, even if they resolve successfully later. You must implement robust error handling for this behavior. Wrap the await Promise.all call within a standard try-catch block. The catch block captures the failure reason from the first rejected promise. This structure prevents the application from crashing due to an unhandled promise rejection. Use this pattern when all parallel tasks are mandatory dependencies. When independent operations must complete regardless of individual failures, use Promise.all.Settled. This method was introduced in ECMAScript 2020 for robust task management. It waits until all input promises are fully settled, meaning they have either fulfilled or rejected. The result is an array of objects describing the outcome of every single task. Successful outcomes are represented with an object with status fulfilled and a value. Failures are represented with status rejected and the specific rejection reason. This allows you to process successful results immediately afterward. You can log or ignore specific failures without halting the entire parallel execution block. Promise.all.Settled is essential for non-critical background tasks where partial failure is acceptable. Promise.race returns a promise that settles as soon as one of the input promises settles. It settles regardless of whether that first promise resolves or rejects successfully. A critical application of this method is implementing network request timeouts. Define a utility function that returns a promise rejecting after a specified duration. Use setTimeout inside this function to trigger the rejection mechanism. pass the original fetch promise and this new timeout promise to Promise.race. If the timeout promise settles first, the operation is aborted immediately. The race promise rejects with a specific timeout error, preventing indefinite waiting. This ensures strict time constraints are enforced on external dependencies. Promise.any resolves with the value of the first promise in the iterable that fulfills. This method is designed specifically for implementing redundancy in web applications. Use it to fetch the same resource from multiple mirrored endpoints or CDNs. If one endpoint is fast, its result is returned immediately. If all input promises ultimately reject, Promise.any rejects with an aggregate error. The aggregate error object bundles all individual rejection reasons together. This provides comprehensive failure diagnostics for every failed attempt. This behavior distinguishes it from Promise.race, which settles immediately upon the first settlement, even if that settlement is a rejection. Apply parallel execution to a real backend deployment scenario. Consider uploading assets to a cloud storage service like Amazon S3. Define an array of upload functions, each returning a promise for a specific asset. Examples include upload CSS, upload JS, and upload images. Use Promise.all for critical assets like CSS and JavaScript bundles. This ensures all mandatory files are uploaded before triggering cache invalidation. If the image upload is non-critical, switch to Promise.all.settled for those tasks. This allows the script to proceed even if a single image fails to transfer. This hybrid approach maximizes deployment speed while maintaining necessary robustness. Parallel execution minimizes perceived latency by eliminating idle time. It removes unnecessary waiting for independent input-output operations. Always quantify performance gains by profiling sequential versus parallel execution. Use the browser DevTools Network tab waterfall view for accurate measurements. Use Promise.all when all tasks are mandatory dependencies for the application state. Use Promise.all.settled for robust execution where partial failure is acceptable. Use Promise.race specifically for enforcing time constraints or selecting the fastest response. Choose the Promise utility that matches your task criticality and failure tolerance requirements.